So indeed, my presentation and the presentation of Nadia go so well together that we have to move my presentation as well. So sorry, Gabriel. So I will speak about stochastic parametrization of model errors using nested model in the context of data assimilation. So I have first a very general slides about data assimilation and about the challenge associated with data assimilation, just to let you know where my presentation actually fits into the big challenges. So as you probably know by now, the data assimilation is about combining observation and model errors in a clever way, in an optimal way. And this is done using and taking the uncertainties in model errors generally into account. So the errors of the model and the errors of the observations. So observation can have errors due to various reasons, instrumental errors, processing errors, but also, and more importantly, the observation do not necessarily represent the same thing as the model. So there are differences in resolved scale and resolved processes. And as you have seen also from the talk of Nadia, errors in the ocean model can due from initial condition, boundary condition, primarily also tidal boundary conditions, as was discussed, atmospheric forcings, bathymetry, as we have seen, and parametrization. And of course, all models are just approximations simply due to the fact that they have to discretize the model errors. There are also discretization errors due to the limited resolution of the model. And there are various challenges in data assimilation. So most techniques actually make some assumptions that we know that are really not true, but they're still useful for most cases. Primarily, they assume that we have that the model error can be represented by a Gaussian distribution function, and but in some cases we need to take into account non-Gaussian aspects. So that's one of the big challenges in data assimilation. And also incorporating new data type is also a continuous challenge, because while we have new data types coming in form of HF radar, CSF salinity, white spot altimetry, and every time we have a new data type, we have to ask ourselves which are actually the processes resolved in these observations, and how can we represent the expected error of these observations. And we have to adapt the assimilation scheme for coupled models. And also, when we're dealing with ensemble simulation, we have to identify the origin of the model errors, and we have to parameterize those model errors. And last but not least, there's a question: what do we learn about the system when we are applying data assimilation? Data assimilation is not a mean by its end. So we have to learn something about. So we want to learn something about the dynamics of the system. What do we learn to improve our model? And of course, the operational context. This system has to be robust and efficient. So in this talk, I more specifically look to the problem of about can we improve the representation of the model error, right? And what do I mean exactly by the model error? So let me just introduce when x is a state vector, so it's all information at a given time t that you need to have in order to make a forecast using your model. So typically it's temperature, salinity, velocity at every model grid point, and if you have this information, you can make a forecast using the model. But of course, your forecast is not correct. Well, it is just an approximation, it's not the truth. And the difference between the truth is called the model error eta, which is here. So knowing the state at one time n, we can make a forecast, but the forecast is imperfect, and that's our model error. And this is often to assume to be a Gaussian distributed random vector and with a model error covariance Q. But actually, quite often, we don't consider this model error. We assume that our model is perfect, in quotes, because we simply don't know much about the model errors. But once we use, what I want to address here in this talk is what can we learn about this model error by considering nested models. So model nesting, there are different ways to perform model nesting. The most common ways is to use one-way nesting. So essentially you run a large-scale ocean model and then extract the boundary conditions to drive a nested model, right? And the large-scale model is actually independent from the nested model. This allows you to run those separately, even different groups. One group can focus to work on the large-scale model and send then the results to another group who runs the nested model using these boundary conditions, right? In a two-way nested setup, there's actually feedback because supposedly the high-resolution model provides a better result because it has simply a higher resolution. And so the idea is to use this information and to replace the output of the in the large-scale model by the result of the nested model, right? So effectively, the model equations are solved twice in this overlapping domain. Once using the COST grid, and once using the high-resolution grid. But we just throw away the solution from the COST grid and replace it by the solution of the nested model, right? But this is actually a opportunity to learn something about the model errors. Because the model equation are solved twice at different resolution, and we can now look to the differences between what was the solution at the COST resolution and what was the solution as a fine resolution. And this leads us to the objective of my talk. So we want to derive an empiric stochastic parametrization of the subgrid-scale process. So it means simply, so subgrid-scale processes means simply I'm comparing the solution, the high-resolution solution to the lower-resolution solution. And the parametrization means I just want to take into account the effect of the high resolution with using simple formulas where I derive the coefficients empirically, and stochastic just means here in this case that I'm addressing a model error which I just represent by a random variable, and then I'm more interested in to look into the distribution, the probabilistic distribution function of this error, right? So, so let's go back to if you have the temperature equation of your model, you can always say that the temperature at time n plus some other model variables allows me to compute the temperature as a next time step, and plus there is some term which represents the model error. And of course, this term, as I showed you before, is a sum of various contributions. And here I look more specifically to the contribution of the limited resolution. Okay. So traditionally, subgrid-scale parameterization are handled in a deterministic way. So, of course, we know that the ocean is a nonlinear system where small scales have an impact on large scales, and therefore we have turbulence closure schemes, which are essentially mixing processes along the vertical. There are also some horizontal subgrid-scale parameterization, which are represented either by a Laplacian diffusion or harmonic diffusion. So Laplacian diffusion simply means that you add a term which is a second derivative of the field, so you just smooth out small scale variations. And the biharmonic diffusion works in a similar, quite similar, except that it's more specific, affects more directly small scales and not larger scales. And these coefficients, these diffusion coefficients, can either be constant or, as shown in the Smagorinsky scheme, depend on the gradient of the field. Okay. But so these are deterministic subgrid scale parameterization, and their objective is to represent the mean effect of these unresolved processes on the flow, right? But it does not tell us something about the variance or the amplitudes of these mean effects. And this is something that we precisely need to know when we make ensemble simulations. So we not need to know the mean effect of the subgrid scale process, but also how strong is the variation. And so the model that we're using is a Ligurency model nested in the CMEMS meridian model, first using just one-way nesting, and in this relatively high resolution model with a resolution of 1.6 kilometer, we nest yet another model, but now in two ways with a quite high resolution, about 500 meter, covering the northwest Corsica area. So we have here a nested ratio of 3. And this, so we're extracting boundary conditions here to apply it to our northwest Corsican model, and in return, these model results are averaged spatially and replace the solution here. And that's what's called the feedback, right? So if you have any questions, you might ask them right now, so don't hesitate to interrupt me if something's unclear. Here just an example of the salinity snapshot. So we see a lot is going on in this model, in this high resolution model. We have a lot of filaments and eddies in this model. And so the general approach is instead of just applying the feedback, instead of just replacing the model results by of the COST model grid by the fine grid, we're actually computing the difference between them. And that's what we call the feedback increment, right? So there's just the difference between the average of the fine grid and minus the COST grid. And formally we can write this feedback increment as an additional term into a model equation, right? And this actually is first an approximation about the model errors due to the limited resolution. And ideally, you want to have compare a coarse model grid with a very, very fine model grid. So here we have just a nesting ratio of 3. So there are, but we're already getting some interesting results based on this. So this feedback increment is then, we save it every 12 hours. We compute also its means and its standard deviation over every 12 hours. And we are looking at this feedback increment for temperature, salinity, and the velocity components. And now this gives us somehow a new window to looking at the model results in terms of what is the additional physics, what is the additional process that the two-way feedback introduced to the COST model grid. So the very first things that we turned to do was to do a UF decomposition, so we can see if there are any spatial structure in this feedback difference. And here we did it for temperature and salinity, and we actually turned out to be a quite flat spectrum. So the first EOF only accounted for 6%, so it's not very useful decomposition. Not very useful to EOFs. But actually for velocity, we see much more interesting structures that some of these differences actually seem to behave like waves. These are coastal trapped waves, and the first EOF actually accounted for almost 50%. And here I show the U component, but the V component behave exactly similarly. And concerning the temporal structure, you can also look to the autocorrelation. The autocorrelation is just a measure to estimate how the error at time 0, for instance, is correlated to the error of any later or previous time. That's the autocorrelation function. And so, of course, so here in x is the time lag, and in y is the correlation. Of course, for a correlation of 0, for a time lag of 0, the correlation is 1, but it drops extremely rapidly off, so it just means that there is almost no correlation in time for the feedback increment in tracers. But for velocity, there's actually quite a much stronger persistence of this feedback increment. So it essentially means that the correction that the two-way nesting gives us to the high-resolution model is actually something that persists over longer time steps for the velocity. So now let's turn on to the more specific idea about stochastic parametrization. So the idea is, can we in some way partially predict the statistical properties of this feedback increment by looking only to the results of the coarse resolution model? So the basic idea is that you should be able to take into account the mean effect of the limited resolution, also if you don't have a two-way nested system, right? So therefore, we look into the case: can we predict these properties just by looking to the result of the coarse resolution model? So we turn into make a linear or nonlinear regression between the feedback increment, or rather the standard deviation of the feedback increment, and the parameters of the low resolution model. So this was done using the test case of the Ligurency model with the nested northwest Corsican model. So first we did a 1 month of spin up, and then we from February we run our model to end of June with this nested simulation. And we divided our simulation into a training data set where we want to derive the coefficients of this parameterization, and a validation data set at the end where we validate our parameterization, and the validation data set is not used to in order to derive the parameterization. Is an independent validation if you want. Okay. So we'll first turn into a very similar case where we do a linear regression. So we try to explain here why is the standard deviation of the feedback increment based on different variables of the coarse model resolution. So x are the different variables. Most of the time x will be just the Laplacian, or the absolute value, rather the absolute value of the Laplacian, and of the corresponding model variable of the coarse model grid. And we also try with a higher order derivative, so the biharmonic diffusion operator and so on. So actually the second derivative and the fourth derivative. And these parameters beta are then just estimated by minimizing the error epsilon. That's very simple linear regression, except that we have now here more variables. So multivariate linear regression you have here. Or we also looked at one form of nonlinear regression where we can introduce some exponents which are noted n1 and n2, but they might actually be fractional exponents. We're not limited. So, and this is here an example which shows why we are doing this and which motivated us to go along this direction. So what you can see here on the left is actually standard deviation of the feedback difference, of the feedback increment, right? So you see in large areas the two-way nesting does not change much the model, but where it does, here, here, and here, actually we are near fronts, right? And this is something that's expected where you have a front then these are the places where resolution matters, and there are the places where you expect the largest difference between a coarse and a high resolution model. Okay, and just simply by computing the absolute value of the Laplacian of the temperature, we see actually structure which resemble quite closely the standard deviation of the feedback increment. And here, just the parameter beta 1 was just the parameter that we have obtained by regression, so that these scales match by construction, but the structure match. But you see that the structure match is actually something quite interesting. And if you see that the Laplacian. So if you compute the derivative on data, or sometimes even on model results, you tend up to amplify noise, and just by applying a spatial filter makes this correspondence even better. Okay. So where here F is just a spatial filter which removes some of this fine scale noise. Okay. So what kind of quantitative assessments can we make? So we want to see how well can we predict this feedback increment. So we are dividing the feedback increment into the regressed version plus an error, and we are trying to see what is the fraction of the variance that we can explain by the regression. Okay. So once we do for velocity a linear fit, we can see that we can explain about 20% of these difference. Using a B-harmonic and a Laplacian B-harmonic does not change much, so you might just stick with the Laplacian. And so this was actually quite encouraging to us, that already 20% of the variability of this field can just be explained by a very simple parametrization. And when we use the nonlinear fit, we can explain about 45%. And that's for the u velocity, and then we have a similar conclusion for the v velocity component. And for tracers, we have quite similar results, so that's roughly 40% of the variability of the impact of the feedback of the two-way nesting can be explained in a statistical sense by using this regression. So here I should stress that I'm not trying to represent the mean effect of the feedback increment, but rather the variability which is introduced. But here for tracers, the nonlinear fit does not improve significantly the results, so you might just stick with the linear regression here in this case. Okay, so in the last two slides of my talk, I will give a little outlook to a CMES project where we look into model nesting, where we look into the question: can we emulate the effect of the feedback using an approach which can be called upscaling? So the general idea is, as in one, you run your model as in the one-way nesting case, where your large-scale model drives a nested model by providing the bounding conditions. But nowadays, most of the operation model already include data assimilation. So the idea would be, why not use data assimilation not just to combine model and observations, but a model and a higher resolution model, right? And so the idea is, can we emulate the effect of the feedback by just using assimilation? So it will still allow us to run the large-scale model relatively independently from the nested model, but every time, say 1 day or 2 days, we could, in the large-scale model, also assimilate the result of the nested model. And these are the first results using this upscaling experiments, just a single step, a single assimilation increment, where we have assimilated the result here in the Lugo-Provençal basin into a Mediterranean model. And it's just the first assimilation, the very fresh first results, and so this is something that we are continue to explore in the future in order to assess the benefit of this feedback through the upscaling approach. So in conclusion, so for two-way nested models, actually the model equations are solved twice in the overlapping region. That's common to almost all two-way nesting frameworks. And this is an opportunity for us to learn something about the model errors due to the limited resolution. And so we have looked in order to derive the statistical properties of these errors using the Laplacian or B-harmonic operator, so essentially just the second derivative and the first derivative. And and we have shown that these coefficients can be derived by regression. And what we learned is we learn about so 40%, roughly about 40% about the variability of this error term simply by linear regression. And so now, using the validation data sets, we've shown to some degree that the coefficient obtained for one time period can be applied for the next time period. But there's also the hope that these coefficients are also independent of different regions, so that this experiment can be done, say, once for a specific region, and then can also be applied in other regions. And in the last part, I looked to as an ongoing project where we look, to emulate the feedback difference, the feedback increment by data assimilation. So that's the upscaling approach. So, thank you very much.